sector, doing very complex buildings in the Netherlands, in the future also in England. You see B to BB. It's first it was from Bauxite to building. Now I work as quality manager for Blitta, so it's from Bauxite to Blitta building. First, I want to tell you something. Aluminum. Aluminum was discovered a long time ago. It's part of the ore bauxite. Bauxite has its name, which comes from Les Baux in France, where it was first discovered. But during the Second World War, it was completely industrialized, and also the new method of making aluminum out of bauxite. Inside bauxite, there is aluminium oxide, also alumina. Aluminium is very light. It melts at 660 degrees centigrade. It's very good for electric current. It's very good for corrosion, although you don't want to think that it's good for corrosion. But when it's a very thin layer of aluminum oxide on the outside, it doesn't get any further and compares to steel or iron. It will rust more and more. It has the atomic symbol 13, aluminum. It's produced out of aluminium oxide. I will come to that back later. And it's a part of bauxite as an ore. It has a very high aluminium oxide is inside bauxite. When it's more than 47%, it's affordable to get it out for a price. It melts normally at 2060 degrees. So when we want to melt it, we add something to lower the melting point. On the bottom part left, you see bauxite. It's the brown-orange color. It's mainly in Brazil, Suriname, and Russia, where bauxite is one. The next part is the white powder. That's aluminium oxide. It's used to make aluminium, but also it's very big part of makeup. So it's used also in makeup. And in the middle part, you see the ingots. That's the end part of aluminium. Here are some pictures of the bauxite. They are pictures from Suriname, where a very large mine is. It's part of the Alcoa Empire. Then when you've got the aluminium oxide out of the bauxite, dus the Al2O3, outside of the bauxite, you can melt it. You put a cryolite in it to reduce the melting temperature. It goes down to 1000 degrees centigrade. Then you get a bath of aluminium oxide. They put in a carbon anode, and then you put current through it, and then the aluminium oxide, the liquid aluminium oxide, splits in aluminium and in oxygen. The oxygen then combines again with the carbon cathode, and the aluminium is heavier than the aluminium oxide, and then it goes to the bottom, and then you can tap it off. It's a continuous process which has a very high demand for electricity, and it goes 24/7. It's same as, for example, the glass industry. It's very hard to stop that process, and it's so it must go 24/7. Here again, some pictures of a melting plant, not remelt, recycling, but melting plant. For example, there's a picture of Norway where they use water power to generate the electricity, and then they get the aluminium oxide, that's the white powder right on top, and then they take it to aluminium, and you see on the bottom part there's a slice of the ingots. You see large crystals, and that has to do by the quick cooling of the aluminium, but that's for the ingots. Energy, normally you would take fossil energy, and as you all know, it's also about CO2 exhaust, That's very important. So when you can use water power for electricity, that's a very good part. Some figures. You see there the bauxite. When I got 4,000 kilograms of bauxite, when I process it, there it remains 2,000 kilograms of aluminium oxide. And now comes the tricky part. It uses a very large amount of electric energy to go from aluminium oxide to aluminium, but also only the half stays. So that's the bad part of aluminium. I can't make it any better, but that's the bad part of aluminium. But when I got aluminium and I got scrap, some kind of aluminium scrap, then it only uses 5% of the initial energy which is used for producing from aluminium oxide to aluminium. So I put it in a bar table. You can see the difference when you go from primary aluminium, that's the diagonal, the primary aluminium, to remelt, so the recycling of aluminium. I will come to that a little bit later. Aluminium is traded worldwide. It's traded in the London Metal Exchange. It's traded in US dollars. So the problem is, you see on the bottom, the cylindrical bar, the bottom part, the gray part, that's the thing you have to always pay, but it's always in US dollars. So the problem is the US dollars and also the conversion to euros. And then the green part is with efficiency and things like that. So that makes the aluminium price what it is for example, for Blitta. When we get a new project, we have to look what kind of profiles that the green part can vary a lot. This is a picture of the ingots. What I earlier said, the aluminium is poured from the melting furnace into casting forms, and they're all the same. They call it in Dutch, they call it een broodje aluminium. It's 25 kilograms of aluminium. It doesn't matter. It's normalized if you put it from Russia, from Brazil, or from America, or something in Europe. It's all the same, the same amount. The applications for aluminium, yeah, it is very, very large number of applications. Drinking cans, foil, ladders, automotive parts, machining parts. You can't imagine everything. It's not the same alloy, but it's in base it's aluminium. We come to that later. Aviation, rail, automotive, machining, packaging. So it's a lot of purposes for aluminium in the several different ways. Unfortunately, we can also make nice buildings. A little bit commercial for Blitta. We make some projects. These are some old projects. These are some new projects. I will come to that a little bit later. But when you look, yes, this one is a building in Almere. It's currently finished, residential, about 30 stories high. This is the main headquarters of ABN AMRO. It will house about 30,000 people in the future. Some of you have been there on excursion. This is the head office of the ANWB, currently also under construction. And this one is a very international known project, the Valley. And this is in Amsterdam and this is in Utrecht. So to resume, we go from bauxite, then we have alumina, also aluminium oxide. We put an energy, and then you got aluminum as a metal. You can extrude profiles, you can recycle it, you can make it as a sheet or a foil. So that's the main issue for aluminium. You can, as you can see, you can use it in transport, automotive, building construction, packaging, electronics, electrical, machinery equipment, and consumer durables. So the use of aluminium is very wide. That's also the problem nowadays, because the demand for aluminium is higher than we can get it. So that's a little bit of a problem. And a lot of aluminium is shipped to the United States and to China, and therefore we don't have a lot of aluminium in Europe as scrap. Now a comparison in energy for some other metals, aluminium, copper, steel, lead, nickel. You see the left graphics, how many energy in terajoules you need to make aluminium. For aluminium it's at 4,700. But when I recycle it again, you see the main advantage for aluminium, that's only 95%. That is the same as I say, only 5% for aluminium. And the other part, we have the same diagram, but then in CO2, that's a very big topic nowadays, how many CO2 is produced to make 1 kilogram aluminium. But this is a very discussable item, because how many CO2 you produce for making 1 kilogram aluminium, that's how you produce it. But I will get there a little bit later. I will get back to that. The non-remeltable materials, you can recycle it, but mostly you don't cycle. So you go in quality or in performance, you go to another part. The same as fibrous metals, for example wood. You can use it, but it never will be the same wood again. Metals, for example aluminium, you can recycle it infinite. So the aluminium you use, the alloy you use, for example the extrusion alloy, if I recycle it 1 time, 2 times, 10 times, 1,000 times, it will be the same. You can't define how many times aluminium is recycled. We've got some two different kinds of aluminium scrap. It's very important. We've got the pre-consumer scrap, the post-consumer scrap. The pre-consumer scrap is directly of waste on the production plant, and post-consumer scrap is, for example, a building which has a new opportunity, it is completely tear down, or another facade is coming to it. Then the aluminium is coming from there. It's post-consumer scrap, and that's also because aluminium has a very long life cycle. It's very hard to get post-consumer scrap. For example, they are now in Utrecht. You've got near the railway station. You've got a building, Katrijnentoren. Katrijnentoren is made 35 years ago. The only thing they do now, they put the old isolated glass out. There come triple glazing in it. So just on the outside, you get new glazing beads. But the complete construction on the inside stays the same. So back again to the CO2, the exhaust from CO2. It's very important that you use sustainable energy, sustainable methods to make energy. For example, hydropower, wind power, or solar power, that are one of the things. When you do that right, this is a sheet, I made it, the red ones, that's the worldwide exhaust of, this diagram is the kilograms CO2 prepared to 1 kilogram of aluminium. And then you see the red ones on the right. They are the worldwide, and you see their figures of 18 kilograms CO2, 20 kilograms CO2 per kilogram aluminium. And that's, for example, India, Russia, China, which are very big CO2 producers. But when you go to Europe, you see then it's getting also a little bit better. You get the yellow ones. They are reducing the CO2 quite a bit. And then you see the green ones, and then it's especially the left 2 ones. You see 1.9, that's when I use 75% post-consumer scrap, and then even 0.5 when I use 100% post-consumer scrap. But that's a CO2, and that's very important, how you produce your energy. But I will come to that a little bit later. This is the loop. In the red square, that's Blitta. So the waste, the aluminium waste, is recycled, made of new profiles. We make their windows, curtain walls, unitized systems. As is on construction site, then you got a use phase. Then after the use phase, the building is demolished or stripped. Anyways, there comes a new facade. It's separated, recycled, can be used again. The yellow crane you see on the bottom part, that is still bauxite made for the purpose of making new aluminium. What I said earlier, the demand of aluminium is higher than aluminium as scrap is available. So it has to be, again, new aluminium. Put this one, and the last one. Also, fossil fuels are used, and because you use fossil fuels, the CO2 exhaust is also a little bit higher. For example, an extrusion plant here in Holland, in Drunen, they are now making hybrid furnaces. So they have a lot of solar panels on the roof. They use that electricity, so it's a hybrid furnace. So everything used to get the CO2 exhaust down. Aluminium itself, it's a very easy metal. It's a solid and then it melts. But when you want to extrude, you can't use a solid metal. You can't use a liquid metal. And when you alloy aluminium with magnesium and silicium, for example, you get a mush state. And the mush state we use for extrusion. This is a part of the diagram for aluminium alloy. For example, you see here how the extrusion process works. As I said earlier, aluminium melts at 660 degrees centigrade. So we heat the billet in the oven to about 480 degrees. Then the billet goes in the container with the die. Then we heat it up a little bit further until 550 degrees. And then it's the mush state we can use for pressing the mush aluminium through the die. Then you cool, and then when it's ready, it has a tensile strength of T2. You can use that. You can look it up in the norms. And normally, aluminium during a time period of 2 years, it will get to a tensile strength of T66. Yeah, we don't have that, so we do artificial aging. It uses then the profiles go in an oven about 8 hours at 180 degrees. So we speed up the process a little bit further. As I said in third, the ingots, that is 100% aluminium. You have to alloy it to make it some properties. You make it a little bit stronger. You use manganese, magnesium, copper, silicium, and zinc to make it the properties of the aluminium a little bit better. And for a total view, you have the cast on the left. You have the cast alloys. And then you have the green one, the forging alloys. That can be forging, that can be extrusion, that can be something else. Then you've got the non-alloyed and the alloyed. And then, for example, here for architectural, for the normal extrusion presses, we use the 6000 alloy, and that's the most common. And you see on the bottom, thermisch hardbaar. That means that we can make we can play with the tensile strength of it. The 6060 alloy and every other alloy is normalized. In this one, in the European norm, the 573-3, you see exactly what kind of alloy elements are allowed and also how broad the expansion can be. For example, silicium, 0.3 to 0.6%, copper just can't go over 0.1%, and that's very strict. And therefore, every time you look at aluminium, this one is how it's made up, what the different alloy types are, and so therefore you can't say how many times it's recycled, 1 time, 10 times. So that's not easy. So here again, for the several alloy groups, the 6000, the main parts of the alloys are magnesium and silicium, and they use also for the tensile strengths or for the machining or for the welding properties of the aluminium. Here are some comparison between the 60-60. You see that it has a tensile strength about 150. And when you stay in the same group, so this is the strongest one, you go to a tensile strength of 250 megapascals. But when you go, for example, the 7,000 alloys, there is a large group. You have more than double tensile strength. It's very often used in for example, the weapon industry or the airplane industry, where you use very tough and hard materials. Here again, what I just said, the artificial aging, you go from T2 to T66, what we use, but normally the architects want something different. They want banded profiles, so we must go somewhere in between. That's then the T64. That's not very tough, but not very weak, but it's in between those both state of aluminium. Then for some project approach, you have a design. Then you want to put that design into reality and within a budget. And then you get an actual building. As you see, we as metal builder have to oblige to very different norms: extrusion, form tolerances, U value, wind and water, fire, emergency and panic, static value, thermal break, local regulations, surface treatment. But that's not all. We have a product standard for curtain walls. We have a product standards for windows and doors, for fire and smoke, panic and escape. We have a special for surface. We have to apply it to Quali-Coat or GSB when it's powder coated. We have to do it for Qualinot when it's anodized. We have some. We have also the alloy, which I mentioned earlier. We have to do it according to that norm. Then the form and place tolerances is also in a norm. And then we are in the community for metal builders in Holland, the VMRG. They have also several demands. And then when you go to, for example, to Europe, you have the CWCT for England, which is very hard again. And lately we have a new norm, the 14024. That's for the thermal break, because that's very important also for the U value of the profiles. So when you go to extrusion, you look symmetry of profiles, same wall thickness. You look at the fixed lengths, what are the minimum order quantities we need, what is the tensile strength. When you go to the form tolerances, here you see it, the 12020-1 and -2, the quantity, the lifetime, how many profiles, how many years, thermal breaks, surface treatment, and others. Here you see, for example, 3.1 certificate. That's something which comes from the automotive industry. The automotive industry wants from every billet you press that we know exactly which profiles are made out of that billet, so that they can trace it completely back if there are some faults or things in the profiles which are not correct. Here are some examples from very difficult profiles. As I said earlier, it's the same as a toothpaste, but when you got some hollow profiles or profiles like that, this gap, or for example these these are heat transforming profiles. For example, they have a very large surface, so they can get the heat which is produced in this one. They can get rid of the heat, but these are very difficult profiles to extrude, especially when you have some high demands on the forms. This one again, also heat transfer profiles. They are, when you look, you say where are they used? For example, audio, video, also in the automotive industry, where you know the beams nowadays in cars. They produce a lot of heat, and the heat must go away. So normally they screw something like that on the back part of the lighting unit. When you got some other performance, when you go to buildings, You got the inside, the outside, floor deflection, wind load, burglary, bullet. So all the things you can imagine. For each project you have some special demands. So again here, what norms, the lead times, what specification for surface treatment, very important for guarantees. Specification guarantee for guarantees in general. What kind of opening sizes do you have on opening methods? What are accessories? For example, the glass. For example, when we went with Geops at the headquarters of ABN AMRO, there were glass panes which weigh about 1,200 kilograms. So it has to be tight inside the curtain wall that it stays in and doesn't deflect. And also for the glass norm. Burglar proof, specification of U value, static value. So therefore communication is very important. The left part is a door which doesn't open again. On the bottom part there's a balcony. Yeah, I don't know. And then the other one, yeah, if you see it correctly, the C didn't fit there anymore. So they fitted the C on the wall, and the other part is then built as designed. So this is built as designed. So yeah, but you can't use the staircase anymore. So that's but the problem is that we as a metal constructor, when we do new profiles, you get the complete traject from die drawing, and then you make the die, then you get the profiles, surface treatment. That's very good, but we only can start when we have a signed off die drawing. And for example, it's very theoretically. Here again the picture which I showed earlier. It's a very difficult profile because when you paid attention, you should symmetrical profile. This profile, it's a profile from the International Crime Court in Den Haag. And you see it's not symmetrical. Here very big wall thickness, small wall thickness. Here a little bit parts of it. Here large, broad. So it was a very demanding profile to get it out. This is the same. This is for the Rotterdam, in Rotterdam, a very big building. You see here the theoretical part is that the picture. Oh. But when it comes out of the die, the first time it looks out like this. So it's very difficult. It's very complex profile. As I said, the toothpaste, but that's the practical part is that it does not come out of the die as we want to, and therefore at each extrusion plant you have people who correct the die. It's just very much experience they have, because when you see the equipment they have for correcting a die, yeah, normally it fits in a lady purse. It's a file, some paper, paper to put it on. So it was very hard. This one is also were very hard profiles for not just for extrusion. For example, this one is a thermally broken profile, but the more this part comes out of the metal, then it's very hard to make a thermal break. This one is the same, so that's for the insulation part. This one is, for example, for the powder coating. When you powder coat an aluminium profile, you put the aluminium profile is positive and the polyester dust is negative. But when you put then the polyester powder over here, then it mostly goes to there and there. But get it in there, it's very difficult. This one is a profile from a TBS clinic in Almere. Very difficult to get the powder coating everywhere we want it. So that's also practical solutions for the examples how you what you come upon. Here again that other profile. The yellow line is the outside, so it's visible, you can see it, but it runs out on the bottom part of the yellow line, and as I said, you got an aluminium silicium alloy, so then there can be also some visible remarks on the profile. So that's it has to be settled. We in the end we turned the profile around. You see here this one, that's over there, and over there. So we turn it around so the profile run out on this surface. So this could cool off very slowly. There's also a detail which is used for anodizing profiles. For this is a 52-degree building in Nijmegen, but at the end it was powder coated. And when you get them powder coating, the powder coated layer is very much bigger than anodizing. So this is, for example, what the powder coating does. And also on this part of on the cover cap, and you could see here and there, it's very difficult to get the complete end situation as the architect wants. So that was in short. Normally I get more time, but that was in short my presentation. Questions, please. Yeah?
What's the thing that you guys stand out for that competitors, for example? Like, what are you very specialized in?
The more complex we like it a little bit more, but because when it's very easy, for example, normal windows, you can also get them from Poland or from Hungary. So that's not yeah, they are low wages countries. So it's very hard to compete with them. So normally the more difficult it is. For example, now we are working in Rotterdam. We do the Baantoren. It's 160 meters high, and it goes up every week, one floor. The outside is granite and windows, but we don't have space. There, when you look at the space, normally, for example, curtain walling or unitized, you say you are building on a post stamp. But in fact, here the round of the post is also gone, so we don't have space. So then it's not just the solution for the technical part, but then the solution lies in the logistical part. So that's but it's we challenge. We don't go away for a challenge. No more questions. So I thank you very much for your time. Thank you.
Well, thank you, Jeroen, for being here, and for Blitta, of course. For you guys, if you don't have any other questions, you can go upstairs to receive your My Future points. If you do have any other questions, feel free to come down to ask them in private. And enjoy your afternoon.